future would be great, and a level of prosperity and hopefully happiness that we can't quite imagine yet.
Something strange is happening under the hood at Tesla, and it's not what you'd expect. While other automakers are caught in a horsepower arms race or distracted by dashboard gadgets, Tesla has gone silent. Literally, inside its latest breakthrough is a component that doesn't scream for attention, yet changes everything. It's not flashy, it's not software, but it may be the reason Tesla just left the rest of the industry in the dust. Built from materials more common in aerospace than the garage, this new piece doesn't just improve performance, it reshapes the very physics of how motion is delivered, and yet almost no one is talking about it. Until now. What Tesla just did to the core of its machine isn't a tweak or an upgrade, it's a redefinition. If you thought EVs had already peaked, think again, because the race just got a new front runner and it's built differently. The carbon-wrapped rotor. Tesla's latest innovation, the carbon-wrapped rotor, marks a major turning point in electric motor engineering. At the core of this breakthrough is the use of high-strength carbon fiber to encase the rotor, a component that traditionally relies on metal for structure and durability. Under extreme rotational speeds, conventional metal rotors tend to deform due to thermal expansion and mechanical stress. Carbon fiber, by contrast, remains rigid and stable even at very high revolutions per minute, eliminating the risk of warping or imbalance. This added stability allows for a more reliable, consistent motor performance, particularly in high-stress applications. What makes this rotor truly revolutionary is how it pushes the limits of speed. The carbon wrap doesn't just preserve the rotor, it enables it to operate at rotational speeds that were previously thought unachievable in commercial EVs. Tesla's rotor can safely exceed 20,000 revolutions per minute, a benchmark well above the industry norm, without suffering structural fatigue or failure. This unlocks new possibilities in motor design, where performance is no longer limited by the physical constraints of metal components under load. Aside from its tolerance for speed, the rotor heralds a wider change in electric motor design. By dispensing with the conventional application of solid metal rotors, Tesla has effectively redesigned the motor's internal structure. Carbon fibers' lightweight and high tensile strength enable a more nimble, resilient core that suits the needs of contemporary electric vehicles. This shift does not simply update a component, it reimagines the material approach at the core of the drivetrain, making the motor not just stronger but also more future-proof when it comes to longevity and engineering flexibility.
It's a very hard thing to do. We actually had to design the machine that makes the rotor.
In the end, the carbon-coated rotor is more than just a new component. It's a manifestation of Tesla's philosophy of engineering. Innovate on the material level in order to discover system-level increases in performance. While the rest of the pack iterates at the edge of conventional motor design, Tesla went beyond the box altogether. It puts Tesla not only at the head of the curve, but in a new category of motor engineering altogether, setting a precedent that might very well remake the electric motor game itself. But just when you think Tesla's breakthrough stops at raw engineering, what comes next proves they've redefined how energy flows through every mile. Efficiency reimagined. Tesla's newest electric motor redefines how efficiently energy can be turned into motion. One of its most impressive qualities is the ability to deliver high torque and powerful acceleration while consuming significantly less energy than previous generation motors. Rather than drawing excessive battery power to generate force, the motor maximizes energy use with precision, making each unit of electricity go further. This creates a driving experience that feels powerful without draining the battery, shifting the paradigm from raw output to optimized performance. A critical part of this energy efficiency comes from dramatically reduced heat generation during operation. In most electric motors, a considerable amount of energy is lost as waste heat, requiring complex cooling systems and resulting in energy inefficiency. Tesla's new motor, however, remains much cooler under stress, which means less energy is diverted to thermal regulation. With less heat to manage, more energy is directed to the wheels. creating a cleaner, more direct transfer of power from battery to motion. For motorists, the advantages of this optimization are real. Energy efficiency means the motor goes longer on a full charge, essentially more miles in a single cycle. Because less energy is spent for the same or greater performance from the motor, charging frequency declines. This generates fewer interruptions from day-to-day use, fewer battery wear consequences over time, and a generally smoother ownership process. The motor not only conserves power, it saves hassle. What Tesla has achieved is developing a system whereby energy isn't merely used, it's honored. Every watt is calculated, with less being lost as heat and more given to motion. This represents a change in what electric vehicles should be able to do. Not merely quicker, but brighter. Tesla's energy discipline focus puts its new motor in the position not just of a performance enabler, but as a long-term solution to one of the most chronic problems in the EV marketplace: how to go further with less. Breaking the price barrier. Tesla's new electric motor isn't just a leap in technology, it's a leap in how EVs are built. The design has been deliberately simplified to reduce the number of components, especially the use of rare earth materials that are traditionally expensive and difficult to source. By minimizing the reliance on these elements, Tesla cuts both material costs and supply chain risks. This streamlined motor design not only makes sourcing easier, but also reduces the need for complex assembly steps, shortening the time and effort needed to put each unit together. Central to Tesla's cost-saving edge is its dedication to vertical integration and sophisticated automation. In contrast to conventional automakers that farm out much of their manufacturing, Tesla produces much of its own production in-house, allowing it close control over both quality and price. Robotic assembly lines and precision casting equipment allow for steady output at high rates with less human error or slowdowns. This automation at the factory level minimizes labor expense while maximizing throughput, simplifying it to maintain growing demand without the equal growth of cost. These manufacturing benefits directly influence how quickly Tesla can supply cars to market, and for how much. With fewer parts, easier assembly, and lower material costs, Tesla can build each car quicker than before. This quicker turnaround enables the company to increase production volumes without sacrificing profit margins. Savings generated during manufacture can be passed on to buyers in the guise of better-priced cars or plowed back to fuel further innovation and expansion. Finally, this production shift is a key part of Tesla's plan, not only to innovate for the sake of innovation, but to make that innovation scalable and available.
While the world is busy taking aim at its CEO, from the showroom to the factory floor, the technology at work is groundbreaking.
By reimagining how motors are constructed and assuming complete control over the manufacturing process, Tesla is making high-tech, high-volume. It's this capacity to balance cutting-edge design with economic efficiency that allows the company to stay ahead, not only in engineering, but in business sustainability too. Legacy automakers left behind. Legacy automakers are facing a fundamental disadvantage in the electric vehicle race, largely due to the way their vehicles are designed. Most traditional manufacturers have attempted to enter the EV market by retrofitting their existing internal combustion engine (IC) platforms, rather than building new electric-first architectures. These modified designs often require compromises, such as bulkier underbodies to accommodate batteries or structural elements not optimized for electric drivetrains. As a result, the vehicles tend to be heavier, less space-efficient, and more complex to produce. In contrast, Tesla's vehicles are designed from the ground up as EVs, allowing for optimized layouts, better weight distribution, and more integrated component placement. But that part of the contrast belongs to Tesla's method and is only implied here. The key issue for legacy brands is that they are starting from behind, trying to reconfigure outdated systems to match the innovation curve of a company that never had to work around old constraints. Another key issue with incumbent automakers is their strong dependence on outside suppliers. For several decades, The conventional automotive manufacturing model has been predicated on outsourcing big systems such as transmissions, battery packs, or infotainment modules to third parties. Though this permitted them to scale and amortize certain cost of operation expenses during the ICE era, it is now a drawback in the EV world, where iterative speed and close coupling are essential. When these manufacturers need to innovate or react to emerging technology trends, they have to sit back and wait for their supply chain to get into sync, something Tesla, with its more centralized model of development, doesn't have to worry about. Furthermore, most legacy vendors are also experiencing difficulty in changing their competencies from combustion-type components to electric systems, hence bottlenecks and delays in product upgrades.
That will be impacted by people upgrading to the 100 kilowatt-hour battery.
The constraints of old factory systems also hinder the response capacity of conventional automakers to evolving needs in the EV market. Most of these lines of production were never conceived with the modular, software-based structure of electric cars. They are instead based on the combustion vehicle logic, which translates to massive retooling, retraining, and logistical restructuring when shifting to EVs. These realignments are time and money consuming and can add new points of failure in the process of ramp-up production. Even when old legacy firms invest billions in new EV initiatives, they tend to be hampered by inefficiencies due to attempts at molding existing infrastructure into novel applications. Their manufacturing processes are rigid compared to the flexibility required by rapidly changing EV technologies. In the end, what distinguishes Tesla from traditional automakers isn't the product, it's the speed of change. Legacy manufacturers work in slower cycles, frequently tied up in years-long design and approval processes, bureaucratic hierarchies, and risk-averse decision-making. Tesla, on the other hand, has shown it can prototype, test, and roll out changes in months, not years. This pace, fueled by an optimized organizational system and an unabated commitment to innovation, makes legacy brands react always and respond never. As a consequence, it creates an increasing innovation gap, not for a lack of talent or funds, but simply because their structures were never developed to move as quickly as the EV age necessitates. Tesla versus supercars. Tesla has done more than just compete with traditional performance brands. It has redefined what speed and power mean in the modern era. With its flagship models, like the Model S Plaid, achieving 0 to 60 miles per hour in under 2 seconds, Tesla has entered a category that was once the exclusive domain of hypercars, from the likes of Ferrari, Bugatti, and Lamborghini. What's more impressive is that this blistering acceleration is delivered without a roaring V12 engine or racing fuel. Instead, it comes from a fully electric powertrain, delivering torque instantaneously with no delay from gear shifts or combustion lag. This level of acceleration was once considered out of reach for a 4-door sedan, and yet Tesla delivers it effortlessly, repeatedly, and with minimal mechanical drama. What distinguishes Tesla from conventional supercars is not only the speed itself, but the manner in which it's accomplished. Supercars use high-revving internal combustion engines, exhaust systems tuned for performance, and aggressive fuel mapping to produce maximum power, at the expense of emissions and fuel efficiency. Tesla cars, by contrast, produce equally breathtaking performance with 0 tailpipe emissions and no gasoline needed. There is no engine roar or turbo lag, only brute, quiet power applied the instant you press the pedal. This completely alters the performance equation. Speed no longer needs to be accompanied by noise, smog, or the hassle of gas internals. Tesla has made extreme performance more sustainable and mainstream than ever. For the driver, that means this transition feels more like flying than driving. Tesla's application of instant torque results in no wind-up or mechanical build. The power is just there, at your beck and call, the instant you need it. This makes for a dreamlike sense of responsiveness during daily driving, whether passing on the highway or accelerating from a standstill. Alongside Tesla's low center of gravity, thanks to its underfloor battery pack location, the vehicle has excellent balance and road holding. even when traveling at speed. The result is a machine that not only accelerates like a rocket ship, but handles with the poise and control of a highly tuned track car without the beating ride quality or frightening noise of conventional supercars.
This wheels-on automation is actually built and designed in-house with Tesla engineers.
Finally, Tesla has turned the formula on its head regarding what constitutes a performance vehicle. Previously, world-class handling and high speed were accompanied by compromises: engine maintenance, fuel expense, emissions, and generally impracticality for everyday driving. Tesla removes all of those. Its cars can equal, and frequently exceed, the acceleration of million-dollar supercars, yet provide the space, comfort, and practicality of a daily driver. This blend of practicality and outrageous ability has redefined performance not as a specialty category, but as something that can be had in a car you can use comfortably every day. Tesla has demonstrated that the future of high-speed driving isn't louder engines or exotic fuel. It's smart, quiet, instant power. But if you think raw speed is Tesla's only ace, wait until you see what's quietly learning behind the wheel, every mile, every moment. Self-driving AI. Tesla's approach to self-driving technology sets it apart through its massive, constantly learning data infrastructure. At the core of Tesla's full self-driving FSD system is fleet learning, a process where every Tesla on the road acts as a sensor, collecting real-world driving data from millions of miles traveled globally. This data includes everything from stop sign recognition and lane merges to unexpected pedestrian movements and weather-related challenges. All of this information is fed into Tesla's central system, where it trains neural networks to recognize, react to, and predict road behavior. This vast network of interconnected vehicles acts as a living, evolving training platform that no other automaker has replicated at this scale or depth. The outcome is an ongoing machine learning cycle that continues to hone Tesla's driving algorithms. Every on-road interaction faced by a Tesla vehicle is an opportunity to learn, not just for the specific car, but for all the other Teslas on the roads. When it encounters an edge case or an anomaly, for example a strange intersection or an unusual road sign, it records the data, labels it, and makes the model better. After updates are made, they are rolled out through over-the-air software updates to the entire vehicle fleet so that all Teslas take advantage of the learning experience. This provides an ongoing feedback loop where the system is continually adapting based on real-world conditions rather than theoretical situations or laboratory tests. What really sets Tesla's FSD development apart from its rivals is that it eschews map-based autonomy. While nearly all the other automakers and startups, Waymo and Cruise among them, are dependent on pre-mapped, geo-fenced zones and LiDAR-centric systems, Tesla's approach is based on generalized perception. Tesla cars learn to drive the way humans do, by observing and learning, not by memorizing a route. This enables Tesla's system to operate in new environments and cope with real-world uncertainty, while competitors tend to flounder outside their precisely controlled test areas. Tesla's AI does not merely memorize, but instead interprets, learns, and generalizes, providing it with a long-term advantage in scalability. In addition, Tesla's neural networks are increasingly advanced, capable now of translating complex 3D environments, identifying patterns in behavior, and making high-level decisions in real time. Not only is this driven by greater data, but by improved data drawn from unpredictable, real-world conditions. In contrast to simulation-based training, which can only teach a car for established scenarios, Tesla's approach regularly reveals new variables and trains the system to process them. As the fleet increases and the pool of data gets deeper, Tesla's FSD becomes stronger, edging closer to complete autonomy with each passing mile. It's not merely about self-driving ability, it's about creating the most intelligent and responsive driver on the road. Tesla's factory domination. Tesla's rise to manufacturing dominance is anchored in its global network of gigafactories, strategically positioned to maximize production efficiency and meet regional demand. Facilities in Texas, Berlin, and Shanghai serve as the backbone of this strategy, each tailored to function as a vertically integrated, high-output hub for electric vehicle assembly. These factories are not traditional car plants. They are hyper-automated, data-driven ecosystems where stamping, casting, painting, and final assembly happen under one roof. Tesla's Texas Gigafactory, for example, is among the largest buildings in the world by volume and is designed for streamlined end-to-end EV production, allowing for faster throughput and more consistent quality. Meanwhile, the Berlin and Shanghai plants play crucial roles in serving the European and Asian markets, cutting delivery times and reducing shipping costs while adapting to local regulatory standards and consumer preferences. One of the most important aspects of the Giga strategy is Tesla's insistence on vertical integration, choosing to manufacture core components such as batteries, drive units, and even custom chips in-house, instead of using third-party vendors. By having the means to make 4680 battery cells, powertrains, and AI hardware in-house, Tesla has greatly diminished its exposure to global supply chain disruptions that have devastated other car makers in recent years. This autonomy not only enables Tesla to have improved quality control, but also provides it with the ability to scale or modify production according to demand without having to wait for supplier lead times. The outcome is a degree of operational flexibility that enables Tesla to act more quickly, innovate more rapidly, and modify product lines more responsively than its peers. Tesla's factory growth isn't merely about expanding what is working, it's also strategic market penetration. The company is aggressively pursuing localized manufacturing in developing markets like India and South America, where the future of EV adoption will be based on local employment, affordability, and lowered import costs. By constructing gigafactories within these markets, Tesla is poised to supply products adapted to local infrastructure, policy, and economic realities. This step is more than a production strategy. It's an extended-term investment in building market loyalty, gaining regulatory support, and making Tesla a bedrock participant in the world's transition to electric mobility. Local production not only enables Tesla to avoid tariffs and trade complications, but also makes its cars more affordable to a broader population by reducing logistics expenses. With this Giga strategy, Tesla is transforming not only the way cars are produced, but also where and why. Every Gigafactory acts as a column of a larger vision, one where manufacturing is as cutting-edge as the cars themselves. With vertically integrated manufacturing, scale automation, and a design plan geared for geographic growth, Tesla is constructing a manufacturing empire that can respond to changes in the market, absorb shocks from around the world, and outrun the conventional production models that have shaped the auto industry for more than a century. The Gigafactory is not a building. It's a testament to Tesla's philosophy to rethink everything, from design to delivery, on its own terms, at a global level. Musk's hydrogen reversal. Elon Musk's recent pivot toward hydrogen fuel marks one of the most surprising reversals in his career, and one of the most talked about developments in the energy and automotive industries. For years, Musk was one of hydrogen's most vocal critics, famously calling it mind-bogglingly stupid and fool cells in interviews and public appearances. His objections were rooted in the inefficiencies of hydrogen production, storage, and distribution, which he saw as vastly inferior to battery electric alternatives. However, in 2025, Musk made headlines by announcing that Tesla would begin exploring hydrogen fuel cell technology, signaling a remarkable shift in perspective. While the reversal stunned many observers, it was not without rationale. It reflected both changing market conditions and Tesla's evolving role in the global energy landscape. One of the main drivers of this shift is growing competitive pressure, especially from Asia. Chinese manufacturers like BYD are rapidly expanding their EV presence aggressively, quickly gaining world market share with volume, affordability, and a focus on innovation. At the same time, Japanese manufacturers like Toyota and Honda have continued to heavily invest in hydrogen, hoping the technology holds longer-term promise to fuel clean mobility. Confronted by mounting saturation in the conventional battery EV segment and mounting credibility for hydrogen as an alternative, Musk's shift seems to be one of careful calculation. By getting into the hydrogen business, Tesla insulates itself from being left out if the momentum changes, or if regulatory support and infrastructure investments start preferring hydrogen in some markets. Notably, this step shouldn't be interpreted as a backtracking of Tesla's fundamental electric vision, but rather as a smart diversification of its clean energy strategy. Tesla has always been more than an automaker. It's a tech ecosystem. Bringing hydrogen to its plans brings it more range in how it achieves zero-emission mobility in various use cases, geographies, and energy landscapes. In markets where hydrogen is more feasible based on government policy or geographic limitations, Tesla can now play along without refashioning its electric-first ideology. This term provides Tesla with optionality in being able to customize its product without compromising on its leadership of the battery EV market. Musk's move into hydrogen is best explained as a long-term hedge, a means of protecting Tesla's leadership in a future that will not be as battery-oriented as was previously assumed. The worldwide conversion to clean energy is multi-layered, complicated, and dependent on regional politics, resources, and technological innovation. By opening the door to hydrogen reluctantly, Musk is not being as self-contradictory as he is being a pragmatist who recognizes that adaptability is the new kind of strength in a changing environment. In this way, he is affirming Tesla's role not only as an innovator of electric vehicles, but as a forward-looking energy giant able to evolve in whatever direction the clean energy movement goes. Tesla Model H. In recent years, as global interest in alternative energy solutions has surged, speculation has emerged around the possibility that Tesla, the world's most influential electric vehicle manufacturer, might eventually venture into hydrogen fuel cell mobility. While the company has made no official announcement, and Elon Musk has been famously dismissive of hydrogen as a power source for vehicles, the notion of a Tesla Model H has sparked intense debate among industry observers and enthusiasts alike. If such a vehicle were to materialize, it would represent a remarkable pivot, or at least a strategic expansion, for a company that has staked its identity on battery electric innovation. The imagined Model H would not merely be a new addition to Tesla's lineup, but could symbolize a dramatic rethinking of the pathways toward zero-emission transportation, particularly in sectors where battery technology may face limitations. At the heart of the speculative Model H would be a hydrogen fuel cell system, an alternative to traditional lithium-ion batteries. Unlike battery electric vehicles, which store energy, a fuel cell vehicle would generate its electricity on demand through an electrochemical reaction between stored hydrogen gas and oxygen from the air. This process, facilitated by a proton exchange membrane, PEM, would split hydrogen into protons and electrons, using the latter to produce an electric current to drive the motors. The only byproduct would be water vapor, making it an environmentally clean technology in theory. The benefits of such a system include fast refueling times and potential advantages in vehicle range, particularly for heavier duty or long-distance applications. However, fuel cell technology is not without its challenges. Hydrogen is notoriously difficult to store safely and efficiently due to its low energy density by volume and the need for high-pressure containment. Additionally, the infrastructure for hydrogen production and refueling remains extremely limited in most parts of the world. If Tesla were to go for a hydrogen vehicle, it would probably go the systems-level route. The firm's highly publicized focus on vertical integration and ecosystem thinking makes it likely that, rather than merely making a hydrogen car, it would instead look to re-architect the surrounding infrastructure in order to support its use. This would include the creation of next-generation hydrogen storage solutions.
It would be very exciting to have autonomous vehicles here in the kingdom.
Like high-pressure carbon fiber composite tanks, which would be necessary to keep energy density and safety intact. Tesla could also launch pilot initiatives or collaborations focused on scaling hydrogen refueling stations, particularly where such infrastructure already has a nascent presence, like California, some areas of Germany, and Japan. Of course, any such development would be in conflict with Elon Musk's years-long skepticism about hydrogen as an energy solution for transportation. Musk has been an outspoken critic of hydrogen fuel cells, deeming them inefficient and economically non-competitive with battery electric solutions. In his opinion, the energy losses that occur in generating, transporting, and converting hydrogen are too high to make it useful in passenger vehicles. However, there are some analysts who suggest even a determined company like Tesla might ultimately consider multi-platform energy strategies, especially in a world that is increasingly diverse in its energy policies and demands. But the Model H is just one piece of a much bigger puzzle, one that connects cars, homes, and entire power grids into something far more ambitious: Tesla's ecosystem. Tesla's ecosystem is a bold reimagining of how energy and mobility can coexist within a seamless, self-sustaining loop. At its core lies a triad of interconnected components: solar panels and solar roofs that generate clean electricity, battery systems like the Powerwall and Megapack that store it, and electric vehicles that utilize this energy for zero-emission transportation. What makes this model so revolutionary is that it doesn't just reduce dependence on the grid, it enables households and businesses to become micro-utilities, producing and managing their own power. A Tesla home can generate its own energy during the day, store the surplus in batteries, and use that power at night, or to charge a vehicle. This transforms the consumer from a passive energy user to an active energy producer and manager, effectively closing the loop between energy generation and consumption. Aside from physical components, the real Tesla differentiator is the brains that tie everything together. All Tesla products are networked and controlled through cloud-based software platforms, which allow for continuous monitoring, software updates, and optimization. Vehicles get performance enhancements and new features delivered over the air, similar to smartphones. Powerwalls learn to optimize energy usage according to time-of-day pricing or predicted weather events. The combination of Tesla's hardware and software enables the ecosystem to act like a living system, continuously learning about user routines, environmental factors, and energy requirements. Artificial intelligence is at the forefront, particularly in energy prediction, charging optimization, and even empowering Tesla's full self-driving cars, which are also part of this combined platform. Tesla's more expansive vision lies far beyond the individual consumer. On a macro level, it seeks to oversee the entire cycle of energy, from production through consumption and even redistribution. That encompasses incorporating its energy systems into national grids to stabilize energy loads via large-scale battery installations such as the Megapack. During periods of peak demand or grid failures, Tesla's distributed storage will be able to supply energy back into the system, averting blackouts and minimizing the utilization of fossil fuel-powered generating stations. While Tesla cars, meanwhile, progress toward being driverless transportation networks, they too will be a part of this cycle, powering up from solar energy and then feeding back to the grid as bidirectional charging and vehicle-to-grid (V2G) systems come online. The firm hopes to see a world where each Tesla product is not only a user, but also a contributor to a circular energy economy. If you found this breakthrough as mind-blowing as we did, don't forget to like, drop a comment with your thoughts, and subscribe for more deep dives into the future of tech and innovation. And hey, don't stop here. Tap the next video on your screen to see how Tesla's new AI is changing everything behind the wheel. See you there.